Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from NCAI Consortium, NCAI ETRI Korea University, VAETKI, Sovereign Korean Large Language Models with Efficient MOE and MLA. This video walks through VAETKI, a new family of large language models designed specifically for Korea. The team built 100 billion, 20 billion, and 7 billion parameter mixture of experts models, with a clear goal: secure national data sovereignty, reduce dependence on foreign AI infrastructure, and provide strong Korean-centric capabilities that can power industrial AI transformation across sectors. The motivation is straightforward. Today's most powerful language models are controlled by a small number of global tech companies. That raises concerns about dependency, data control, and how well these models really understand local languages and cultures. For Korean, many foundation models struggle with subtle linguistic features, cultural context, and domain-specific needs. VAETKI aims to change that by providing a domestically controlled, high-performance LLM that can be deployed across Korean industry and the public sector. VAETKI isn't a single model, it's a family. There are three main sizes: a 100 billion parameter flagship, a 20 billion mid-size model, and a 7 billion small model. All of them use a decoder-only transformer architecture, but with mixture of experts feed-forward layers to scale efficiently. The architecture and training methodology are shared across scales, so behavior is consistent, while each size is tuned for different deployment environments, from large data centers down to more constrained setups. Before diving into the architecture, it's useful to see where VAETKI stands. The 100B model, VAETKI 100B A10B, is competitive with strong open mixture of experts baselines. It shines on Korean benchmarks like Click and Cobalt and shows strong instruction-following performance on IFEVAL while using a carefully controlled activated parameter budget. This positions VAETKI as a practical, efficient foundation model tailored to Korean needs. At its core, VAETKI is a decoder-only transformer, but with two key twists. First, it uses fine-grained mixture of experts layers in the feed-forward blocks, so only a small subset of experts is active per token. Second, it replaces standard multi-head attention with multi-latent attention, which compresses key value states to save memory. On top of that, it interleaves local and global attention patterns, giving the model long context capabilities without paying the full quadratic cost at every layer. Multi-latent attention already reduces memory by compressing the key value context, but it doesn't automatically fix the quadratic compute cost. VAETK tackles this by interleaving local and global attention. Most layers use local sliding window attention, and only every sixth layer performs full global attention. This 5-to-1 ratio is based on observations from Gemma 3 that you can thin out global layers without hurting perplexity. Combined with carefully tuned rotary embeddings for local and global heads, this design cuts KV cache size by about 83% at 128,000 tokens and yields roughly a 40% training efficiency gain at the 100B scale. The feed-forward networks use a fine-grained mixture of experts design. In the 100B model, each MOE layer has 128 experts, plus a shared expert. For each token, the router activates 8 experts, computes a weighted sum of their outputs, and then adds the shared expert's output. This keeps the effective hidden size consistent with a dense FFN. Routing is driven by sigmoid-based affinity scores and a global auxiliary loss, plus a conventional load balancing loss, both with small coefficients. This encourages experts to specialize while avoiding collapse onto a few experts. Training a 100B scale MOE model efficiently requires aggressive use of low precision. VAETKI uses FP8 for linear layers in both dense and MOE blocks, powered by NVIDIA's transformer engine. To keep training stable, the architecture adopts Peri-LN and a zero-centered RMS norm variant, which help keep activations well-behaved. The team also found that blockwise FP8 scaling can be unstable at the very start of training, so they delay it, starting with safer scaling and switching to blockwise scaling later for better throughput. VAETKI uses a 135,000 token byte fallback BPE tokenizer, trained to reflect the language mix in the data. Over half the vocabulary is Latin-based, but about 20% is dedicated to Korean, including the full Hangul syllable block and Jamo characters. This supports both modern and historical Korean text. For code, tabs and whitespace patterns are explicitly tokenized to preserve indentation. On the interaction side, the chat template introduces a think block, where the model can generate internal reasoning, and a clear/think boundary before the final answer. This lets the model reason explicitly without mixing that reasoning into the user-facing response, and can be disabled for heavy tool use scenarios. Training VAETKI required serious infrastructure. Just over 1,000 NVIDIA H100 80GB PCIe GPUs on the Naver Cloud MLX platform, with about 85% average utilization over roughly 4 months. The cluster had only 4 InfiniBand lanes available for tensor communication, less than frontier setups, so the team used a hybrid strategy: NCCL for most GPU collectives and glue for some cross-host operations to relieve pressure on the fabric. Parallelism combined tensor, pipeline, expert, and data parallelism, with sequence parallelism added later to handle long context training efficiently. On the data side, the team started from about 20 trillion tokens of raw text, including Common Crawl-style web data, code from sources like the Stack v2, math and science datasets, and large Korean corpora from AI Hub. From this, they curated a 5 trillion token subset through a 7-stage pipeline: heuristic filtering, deduplication, perplexity-based filtering, model-based quality checks, removal of harmful content, de-identification of personal information, and spam and noise removal. They also ran 12-gram decontamination against major benchmarks to reduce test contamination. Pre-training follows a 3-stage curriculum. Stage 1 focuses on broad language and world knowledge at a 4096 token context, using a constant learning rate and progressively increasing batch size up to around 55 million tokens effective batch. Stage 2 shifts the mix toward reasoning-heavy data, including STEM and code, and introduces fill-in-the-middle training on about 60% of the data to strengthen bidirectional reasoning. Stage 3 extends the context window, training on sequences up to 32,000 tokens, with position interpolation applied to global attention to generalize to long contexts while keeping local attention stable. An interesting design choice is a mid-training phase, where the model is exposed to instruction style and conversational data before formal post-training. This phase uses data that was curated for alignment, but didn't meet the strictest quality thresholds for final SFT. By mixing this into late pre-training, the model becomes familiar with chat formats and instruction patterns early, which makes the later supervised fine-tuning and preference optimization stages more efficient and stable. After pre-training, the VAETKI goes through a 3-stage post-training pipeline. First, a reasoning-centric supervised fine-tuning stage, then a high-quality SFT stage, and finally, direct preference optimization. Altogether, the team built around 8 million triplets of queries, reasoning paths, and responses. On top of that, they added 17.6 billion tokens of in-house curated data focused on multilingual support, Korean cultural knowledge, and mathematical reasoning. This combination is what turns the raw language model into a practical assistant tuned for Korean and neighboring languages. The first SFT stage focuses on reasoning. About 3 million samples emphasize code, math, and logical reasoning, helping the model learn robust reasoning structures in a chat format. The second SFT stage is more selective. Roughly 2 million high-quality samples are kept after strict filtering. For math and code, reasoning paths are synthesized and verified to guarantee correctness. Queries are filtered using a clarity tagging model that scores how well-defined and self-contained they are, while responses are evaluated by another LLM, keeping only high-scoring outputs. The dataset is multilingual, with controlled style distributions in Korean, Chinese, and Japanese, and includes a slice of multi-turn dialogues and tool use scenarios with many distractor tools to train robust tool selection. Beyond open data, the team constructed 17.6 billion tokens of specialized datasets with support from Korean government agencies. This includes Chinese and Japanese corpora to strengthen multilingual performance, Korean cultural heritage, and Q&A built from authoritative dictionaries and academic literature, detailed step-by-step math reasoning problems at middle and high school level, and multi-turn instruction-style dialogues. These datasets are designed to give VAETKI deep grounding in Korean culture and solid reasoning skills, not just surface-level fluency. During supervised fine-tuning, the objective is standard next token prediction, but applied selectively. Loss is computed only on the model's own outputs, including the reasoning path and final answer, while system prompts and user inputs are masked out. This focuses learning on reasoning quality and correctness instead of prompt mimicry. The SFT phase, covers about 430 billion tokens, with a relatively small effective batch size and a conservative learning rate schedule. To keep the MOE structure stable, router parameters are frozen and the load balancing loss is reduced, so experts don't reshuffle during alignment. The final alignment step uses direct preference optimization. The team built about 200,000 preference pairs, where each prompt is paired with a chosen response and a rejected one. Chosen responses are either correctness verified or highly rated by an LLM as a judge, while rejected ones capture typical failure modes like wrong answers, repetition loops, or unnecessarily long and unstable reasoning. DPO then directly optimizes the model to prefer the good responses over the bad ones, with a KL penalty to keep it close to the SFT reference. Router weights remain frozen, so the expert structure learned earlier is preserved while the outputs are refined. To understand how VAETKI performs, the authors evaluated on a broad suite of benchmarks. For Korean, they use KMMLU Pro for professional knowledge, Click and Cobalt for linguistic and cultural competence, and HRM8K for math reasoning. For English, they include MMLU Pro, GPQA Diamond, and HLE to probe general and high-level reasoning. Instruction following is measured with IF Bench and IF Eval. Safety and alignment are tested with XS Test and OR Bench for over-safety and over-refusal, Salad Bench for compositional attacks, and Strong Reject for jailbreak robustness. Table 4 compares VAETKI 100B A10B with a strong open MOE baseline, GPT OSS 120B medium. VAETK has slightly fewer total parameters but activates about 10 billion per token versus 5.1 billion in the baseline. On Korean benchmarks, VAETK clearly wins on a Click and Cobalt, showing strong linguistic and cultural understanding, but lags on KMMLU Pro and HRM8K, especially for structured reasoning. In English, it trails the baseline on MMLU Pro, GPQA Diamond, and HLE, confirming a reasoning gap. However, on IF Eval, which measures instruction following, VAETK scores 86.0, beating the baseline's 83.6. This suggests the model is particularly good at following user instructions, even if its deep English reasoning still has room to grow. Safety-wise, VAETKI 100B A10B reaches a similar overall robustness level to the GPT OSS 120B baseline on standard unsafe prompts. It maintains high refusal rates on clearly harmful inputs. Where it stands out is utility. On safe prompts in OR Bench and XS Test, VAETKI responds much more often, meaning it's less likely to over-refuse benign requests. That's important for real-world usability. The main weakness is on Salad Bench, which uses sophisticated compositional attacks. Here, VAETKI underperforms the baseline, signaling that more work is needed to harden the model against advanced adversarial prompting while keeping its good behavior on everyday queries. The authors also evaluate a smaller 7B scale MO model, VAETK 7B A1ME. It activates about 1.2 billion parameters per token, and is trained on just 1.86 trillion tokens, far less than comparable models like Granite 4.0H Tiny, which uses 23 trillion. Despite this, VAETK 7B is competitive on multiple Korean and English benchmarks, and nearly matches Granite on Math 500, a math reasoning benchmark. This suggests that the architectural choices and data pipeline scale down reasonably well, even under tight compute budgets. The authors are clear about VAETKI's limitations. First, there is a noticeable reasoning gap on difficult English benchmarks like GPQA Diamond and HLE, pointing to the need for better high-level reasoning data and training. Second, the training environment had only 4 InfiniBand lanes for tensor communication, forcing a hybrid NCCL glue setup that likely limited efficiency compared to frontier systems. Third, evaluation so far focuses on general benchmarks. Detailed tests in specific industrial domains like manufacturing or finance are still early. Finally, the current multi-latent attention plus local global interleaving design doesn't play nicely with standard context parallelism frameworks, so they had to disable that dimension, limiting sequence length scalability compared to full 5D parallelism. Looking ahead, the team plans to improve reasoning by generating higher quality synthetic data and applying stricter verification to reasoning paths, especially for benchmarks like GPQA. They also aim to scale up to a 200 billion parameter MOE model and extend VAETKI into multimodal territory, leveraging the consortium's multimodal datasets. On the application side, they want to build industry-specific variants for manufacturing, finance, and services, providing concrete AI transformation solutions. And on the safety front, they plan to strengthen defenses against complex adversarial attacks, while preserving the model's good response rate on safe prompts. To wrap up, VAETKI is a serious step toward sovereign AI for Korea. A family of 100B, 20B, and 7B mixture of experts models, tuned for Korean language and culture. Architecturally, it combines fine-grained MOE with multi-latent attention and local global interleaving to dramatically reduce KV cache size and improve training efficiency. The models show strong performance on Korean benchmarks and instruction-following tasks like if-eval, while still trailing top baselines on the hardest English reasoning tests. Underneath, there's a carefully designed pipeline for data curation, multi-stage pre-training, supervised fine-tuning, and preference optimization. Together, these pieces make VAETKI a practical, efficient foundation for Korean-centric AI applications and a platform for future scaling and multimodal expansion.